Yay. That means just lecture and get out of here. And next week we will have 3 labs and an exam. The way the days fall, we try to make it work out to where we're finishing up some things right toward the end. Just kind of going over schedule stuff with you. We got this week. We're going to cover 4 sections or mini sections tonight. Not the complete section in any of them, but the material we'll cover tonight. We'll do labs on next Monday. You will have a Canvas quiz over these. That Canvas quiz kind of serves as a practice test since it's the only material that's going to be on the exam. So you can expect your exam to be a lot like that Canvas test. And that'll be next week. And then you won't have anything to do that following week. You won't have like a Canvas quiz or anything going on. So that won't interfere with your trick-or-treating or yard rolling or whatever it is you're doing. So then the next week we'll cover a pretty good bit of material there, and we'll have 3 class meetings of lecture. And then our last exam, like classroom exam, will be that Monday before Thanksgiving, and then that ends our material for the course. And then we would meet again the next Monday after Thanksgiving and have a review for the final exam. And then the final exam is December the 11th, that Monday night. So second half really rolls by pretty quickly, and works out pretty nicely in your favor. I think the material we'll cover tonight is kind of the basis of what exam 4 will kind of cover. But we just kind of lump this part together, make an exam out of it, and then the other part, lump it together, make an exam out of it. So we got just a few more weeks in class. It really has flown by. Doesn't seem like we'd be talking about the end yet, but we are. So,
what about our last test grades?
Your last test grades? Yes, I have them graded, and if you can hang around a few minutes after we finish lecture tonight, I can pass those out to you. That'd be all right. That good? And with your midterm grades, what you saw on that's with nothing dropped and everything averaged like it is. And so whatever that letter grade was, that was just taking your average straight from what you had and not dropping any grades. You understand that when I do average at the end, I drop your lowest test grade, replace it with your final if it's higher. That's how that's dropped. Your Canvas quizzes, I drop your lowest one of those, and then I drop 3 lowest lab grades. Okay, so your average can definitely go up toward the end there when I do that. But midterm grades, I don't drop anything. Just this is what you've scored so far. This is where you're sitting.
So if our final is a higher exam.
It's higher than one of your. Then it still counts as the final, but it doesn't replace one of your test grades. Your test, I'll take the highest, like your final exam. Let's say you made all 80s on exams 1, 2, 3, and 4, and then you made a 75 on the final. That 75 will count as your final exam, but it won't change any of your other exam grades. But if you made a 70 on all the tests and then made a 75 on the final, I would replace one of those exams with the 75 from the final. That makes sense? Okay. So whatever your lowest exam grade is, if your final exam is higher than that, I will replace it with it and then take the new average from there. So that can be a lot of, a good score on that final can swing your grade quite a bit. And I won't kid with you, the final's kind of tough, but that's why I build in that day, that week before that, to kind of help you study for it, know what to study. And we'll go over a practice final or 2 as well. All right, so let's get going with multiplying polynomials. So we're in section R.3. We've done parts of R.3 throughout the course. Tonight we're going to talk about multiplying polynomials. So some basic stuff. We'll start with an example like this: 3x times 4x plus 3. And so what property does that look like? I remember from maybe an algebra class. Distributive property. Yeah, we're going to distribute this 3x to both pieces in there. So it's 3x times 4x. So 3 times 4 is 12. What's x times x? X squared. So add the exponents, really what you're doing there. And then 3x times 3 would be 9x. And you've multiplied a monomial, one term, times a binomial, two terms. Get that result. Pretty easy stuff so far. Let's throw negative 5x squared times negative 2x minus 8. A lot of negatives in there, so signs, big part of this. So a negative 5x squared times negative 2x minus 8. What do we do? All right, when you distribute there, you get positive 10. Negative times negative is a positive. X cubed, third power. And then, what's after that? Yeah, 40. Negative 5 times negative 8. They treat that minus sign as if it's a negative 8. And make that positive 40. And then the x squared just carries over. There we've got that. Just using distributive property. Distributive property is the vehicle that we're going to drive throughout this entire lesson. X plus 3 times x plus 4. You may have learned in high school algebra something called FOIL method, which is wonderful, and it works, but only for binomial times binomial. Doesn't work for anything else. Distributive property works every time for anything. So I don't call it FOIL method. It is FOIL method. If you learned it that way and you remember doing it that way, that's fine to do it that way. I just do it as distributive property. How many terms are in this first piece? 2. So that means I'm going to distribute 2 of them. I'm going to distribute one at a time. X times x, x times 4. And then I would distribute the 3. 3 times x and 3 times 4. Okay, so when I distribute the x times x is x squared. X times 4, 4x. And then I'm going to distribute the 3. And it's a plus 3, so I'm distributing positive 3. So positive 3x, positive 12. And then we simplify if possible. Yes, these two in the middle are like terms. So that'd be x squared plus 7x plus 12. So it's just distributive property twice. Same thing as FOIL method if you learned it that way back in an algebra class you had before. It's just distributive property over and over. So if you had like something like x minus 7, parentheses, 2x plus 5. Again, it's just distributive property. We're distributing x, and then we're distributing negative 7. Just 2 times. X times 2x, 2x squared. X times 5, 5x. And then distribute the 7. It'd be negative 14x and negative 35. And then combine the like terms. We got a positive 5x and the negative 14x in the middle. They'll combine together to get us negative 9x minus 35. Multiplying a binomial times a binomial. It's just distributive property twice. Two x plus 7 times 2x minus 7. 2x minus 7. Right. 2x plus 7 times 2x minus 7. What are we doing? Is this any different than the previous problems? Not a bit. They look, the two binomials look very similar. Works very similar. So let's do that and see what happens here. So 2x times 2x, 4x squared, 2x times negative 7, negative 14x. And then we distribute the 7. 7 times 2x, positive 14x. And then 7 times negative 7, negative 49. What happens to those pieces in the middle? They go away. They cancel each other out. A negative 14 and a positive 14 cancel each other out. So we get this 4x squared minus 49 left over. Nothing really, this is a special thing. It's called a difference of squares. The final answer is, we'll talk about that more in the next section when we're going backwards. We're starting with the polynomial at the end and going backwards to the 2 parentheses pieces, and we'll teach you how to do that. But it's a difference of squares, what it's called. But it's easy to, once you start seeing some of this stuff, it's going to make some sense when we start going the other direction. All right. Say we had 2x minus 3 times x squared plus 7x minus 9. So a little bigger problem. But what are we doing? Same thing. It's just a little longer. Okay, I'm going to show you what I usually do when the problems get longer. I try to organize myself in a little better way to make my life a little easier. So I'm going to distribute the 2x first. 2x times x squared, 2x cubed, 2x times 7x, 14x, 2x times negative 9, negative. It's 14x squared, sorry. Then that'd be negative 18x. Then when I distribute the negative 3, that's negative 3x squared. I'm going to write it underneath that one. And then I distribute the 3 to the 7x, negative 3 to 7x, that's negative 21x. And then negative 3 times negative 9 is positive 27. Stacking it up like that allows you to get the like terms together. Makes it, to me, organizes it in a way that's quicker and easier to add up. And then you're just going to add those pieces together. 2x cubed just comes down because there's nothing to add with it. 14x squared minus 3x squared be 11x squared. Negative 18 and negative 21. Negative 39. And then the 27 doesn't have anything else like it. So when the problems start getting longer, I like to stack them up with the like terms. Just makes it a little easier to do at the end. It's not necessary. It also kind of saves me a little bit of paper sometimes. Do it that way. Show it now. So distributive property, it's just distributive property again. If you had a trinomial 3 terms times something else that had 3 terms, it's just distributive property 3 times. So the longer the problem gets, it's just distributive property more times. So it really doesn't ever get any more complicated as far as the work goes. Just the length of the problem gets a little bit bigger sometimes. We won't get just incredibly large in here. Let's look at this one. X plus 5 quantity squared. So I'm squaring. What's it mean to square something? Multiply it times itself. So if I rewrite this problem to x plus 5 times itself, because that's what it means to square something, is multiply it times itself. What's that turn into? Almost. Don't forget the middle pieces. So it turns into a problem that's just like what we just done. It's still distributive property over and over. There are some shortcuts to being able to multiply binomials out like this, but I don't think it's saves you so much time that you're going to be able to save up vacation days because of it. So, I just did the distributive property. X times x, x squared. X times 5, 5x. And then distribute the 5. That's another 5x. And then that's a plus 25. So in the middle, we've got x squared plus 10x plus 25. So don't forget that middle term that's going to happen there. The only time the middle term is going to cancel out when you're multiplying binomials together is if they're exactly the same, but one's a plus and one's a minus. That's the only time the middle term will cancel out. So that's a good thing to kind of remember. Let's do 2x minus 3 squared. So what's it mean to square something again? Multiply it times itself. So 2x minus 3 times 2x minus 3. Exact same thing over and over. Don't overthink it. Just distribute. That's all you've got to think about doing. 2x times 2x is 4x squared minus 6x. Another negative 6x. And then a positive 9. 4x squared minus 12x plus 9. Just in case you're interested, the shortcut for squaring a binomial, and it only works with binomials, is square the first piece, square the last piece, and that's the front and the back. X squared is x squared, 5 squared is 25. And then to get the middle piece, you multiply the together. 5 times x is 5x, and then double it, and that gets us 10. Over here, if I square 2x, 2 times 2 is 4, x times x is x squared. If I square 3, that's 9, right? The middle piece, what's 2 times 3? 6, and then double it is 12. So the shortcut is to do that. But by the time I've done all that, then I just distribute. Yeah, I just work the problem with distributive property. So I don't really ever teach these shortcuts to my high school students anymore. It's one of the, it's not really a standard. They're supposed to recognize it. They don't have to actually apply it in any way, shape, or form. The problem is, can you multiply that out? Whether you use a shortcut or not, can you multiply that out? I don't think the shortcut's a shortcut. It doesn't make it any faster. So that's why I don't really put a ton of emphasis on, hey, memorize this shortcut. It's going to save you time. No, it probably won't. I don't think it. Yeah, it's one of those things where I just don't think it's a shortcut to help you. Now, this problem, what letter will x plus 3 and x minus 3. Now, this one I think is worth the recognizing the short end of this one. If we just work it the regular way, x times x is x squared minus 3x, and then plus 3x and minus 9. We get x squared. These guys cancel each other out, and so it's x squared minus 9. I think it's worth recognizing that, if the two things you're multiplying together are exactly the same except for the plus and the minus in the middle, that it shortens up to square the front, square the back, minus in the middle. I think that is a shortcut worth taking, so that, like if I had something like 5x plus 9 and 5x minus 9, those are larger numbers. 5 times 9 is 45, and 5 squared is 25, 9 squared is 81. So you're dealing with larger numbers there. The shortcut, because the factors are exactly the same, except for one's a plus and one's a minus, would tell us, the answer is 25x squared minus 81. If you did it the long way, i.e. no shortcut, you get the same answer, because 5x times 5x is 25x squared. 5x times negative 9 is negative 49 on 45x. And then positive 45x, negative 81. You get the same answer. Shortcut's nice. It didn't save us a whole minute, even on the problem. So Shortcuts are great, but I don't necessarily think there's something you need to memorize. That I always do that. Just remember, hey, it's distributive property. Do it, and you're going to be okay. Let's do one more here. If we had x plus 2 cubed. So if we're going to cube something, what's that mean, dude? 3 of them. X plus 2 times x plus 2 times x plus 2. Ooh. Now, there's a steakhouse down close to where I live that has a challenge if you eat it in so much time. You know how you eat a 72-ounce steak? One bite at a time. This is a big steak, okay? We got to eat it one bite at a time. Don't try to do it all at once. Pick you 2 of them and work those, okay? I'm going to pick these 2 right here. And then I'll distribute the last one at the end, okay? So I'm going to multiply these 2 together. X times x, x squared, 2x, and then distribute the other 2. So 2x again, and 4. And then work that part. That's going to be x squared plus 4x plus 4. Put that in parentheses, and then I'm bringing down the x plus 2 that I had up there that I haven't used yet. No, because they're both positive. That's the difference. If one had been a positive and one a negative, then yes. But because they're both positive, they don't cancel each other. Now I've got what do I do now? Distribute. Same old thing again. It's just a little longer. Okay. So x times x squared is x cubed. X times 4x is 4x squared. X times 4 is 4x. And then distribute the 2. That's 2x squared. And I'm putting a plus sign in front of that because it's positive. That's the whole reason I'm putting it there. And then plus 8x. And then plus 8. X cubed. 6x squared. 12x. And 8. Yes, absolutely. If you tried to do x times x times x and then do 2 times x and 2 times, you get lost very, very quickly. I would get lost. Yeah, a lot of places. There's a lot of operations there. You're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 operations that you did there doing it this way. If you tried to do them in an unorganized way, 17 steps in anything could very quickly be messed up. I mean, the 17 steps, if there were 17 steps in tying my shoes, I don't think I'd have ever learned. Okay. So that's the idea here. All right. So multiplying them out, that's the first direction. Now we're going to work the opposite direction. We're going to start with a polynomial and break it into pieces. Okay. So this is section R.4, factoring polynomials. And the good thing is I think there's rules to factoring. Rules to factoring. The first thing you want to be sure of when you start trying to factor a polynomial is that it's in descending order. What I mean by descending order is highest exponent on the left and then go down. So an example of that would be like x to the 4th plus 3x cubed plus, 7x squared plus 5x plus 10. That's in descending order there. Starts with the highest exponent, goes down. If you're going to try to factor something, you want it like that. Okay? We probably won't factor anything that extremely large, but that's the idea. The descending order is what I'm after there. Okay? Now, once you have something in descending order, the second thing you want to always look for, and the first factoring step, is a greatest common factor. Okay, greatest common factor, and I'll refer to this as the GCF from here on out, probably. Greatest common factor, GCF. So that's the biggest number or variable group that will go into a term. Okay, so like the greatest common factor between 8 and 12 is 4. That's the largest number that will go into 8 that will also go into 12. That's what I mean by greatest common factor. The biggest number that will go into those two numbers or more, 3, whatever, it depends on the size of the polynomial. Okay. Once you've pulled out the greatest common factor, you want to pull that out to the front, and then the next step is to look at what's left and count the terms. The number of terms that are left is going to determine what method you will use to factor. Okay? If there are 4 terms, you're going to use a method called grouping. And we'll go over that and definitely do some examples of that. If there are 3 terms, we're going to use what I call the X method. When I learned to factor in high school, I didn't learn the X method way. I learned guess and check, which may be how you learn too. And if you're good at guess and check, it's great. If you're not very good at guessing, it could take forever. Okay, the X method is a little bit more focused, kind of narrows down the number choices that you might have. So that's why I like using it now, and I'll show you how to do that. And it's kind of like guess and check, but more systematic. So you're not spending 20 minutes trying to figure out what could be multiplied to be 20. Am I using 1 and 20, 2 and 10, 4 and 5? Which ones of those am I using, and that sort of thing. So you could have a lot of guesses and be wrong. If there are 2 terms, a couple of things that could happen. It could be a difference of squares. I kind of made reference to that earlier. The key is that it's squares. To know that difference of squares is the method, you'll have things that are square, like square numbers, 4, 9, 16, 25. The square numbers, like 2 squared is 4, 3 squared is 9. That's where I'm getting those. Another thing that could happen is a sum or difference of cubes. There's the difference of squares. I'm going to show you how to rewrite the problem, recognize that, and then there's a pattern. The sum and difference of cubes, there's a pattern that you just almost have to, there's no almost, you do have to memorize the sum and difference of cubes pattern for factoring. But once you memorize that pattern, any sum or difference of cubes works that way. Same thing with differences of squares. If you can see that it's a difference of squares and you can rewrite it as that, then the pattern always works for it, and you just memorize that pattern. So with its 2 terms, we've got these 2 possibilities, and we'll recognize those based on really the exponents on the variable. If the exponent is squared, it can't be a cube. It's got to be squares, right? If the exponent is a 3, then it's probably a sum or difference of cubes. Okay. All right. So we're gonna take our rules of factoring, and we're gonna go down through them with each problem that we do. Okay. First thing we got to have is it's in descending order. Then we're going to get a greatest common factor. Talk about that first because that's the tool that you'll use for everything else. And then we'll talk about what happens when you've got more terms to deal with. can you factor it any further? So we're going to look at that as we go through section R4. This is definitely the longest section of the night. The next two are not nearly as long and not nearly as difficult as this one. This one's a little tougher. Okay. All right. So we're going to factor the polynomials. That's our instructions. So example A, 5x plus 10. Something real simple to start off with. Okay. Now, if we're looking at this problem, is it in descending order? Yes, we got 5x, that's x to the first power, and then the 10 doesn't even have an x. So that's in the right order. X is in front, plain number in the back. That's the right way. Okay, so it's in descending order. Then we need to look at greatest common factor. So we're looking at the term 5x and the term 10. Okay, what number goes into 5 that also goes into 10? 5. 1 also does. Which one's bigger? 5. Thus, the greatest common factor would be 5. Then you look at the letters. Well, 5 has an x, but 10 doesn't have an x. So can they be common? Absolutely not. So the greatest common factor for this problem is 5. So you put that out in front, and then you put a set of parentheses. And then this is what you got to think. Okay, if I divided this by 5, what will be left? X. If I divide this by 5, what would be left? 2. So I have an x plus 2 in the parentheses. X plus. Okay. All right. Greatest common factor comes out to the front, and then you look at what's left. All right. For argument's sake, we'll look at what's left. How many terms does it have? 2. So if we can factor it and it's got 2 terms, it would have to either be a difference of squares or a difference of cubes or a sum of cubes. Is there a squared on that x? No. Is there a cubed on that x? Can't be either of them then. So that means we're done. We stop. That's the factored form for that polynomial. Okay. Another one that's a little bit more, kind of stepping it up a little at a time here. We got 6x squared plus 8x. Is that in descending order? Yeah, we got the x squared first and then the plain x next. There's not a term that doesn't have an x, so that's in order. The next thing we want to look for is the greatest common factor. So I look at the numbers first, 6 and 8. 2 goes into 6. 2 also goes into 8. 6 goes into itself. Does 6 go into 8 evenly? No. So 2 is the biggest one. Okay, so we're going to use 2. Then we look at the first term. It's x squared. How many x's is that? It's 2 of them. The second one has how many x's? 1. That means how many do they have in common? No. 1 in common. This guy's got 2. This guy's got 1. You could pair up one of them. That would be that's what I mean by in common. So there's 1 x that's in common. So the GCF is going to be 2. That was the number that you guys said. And then there's 1 x in common. So we're going to pull an x out with that. How many times does 2 go into 6? 3. How many x's did I take out? 1. So how many are left? 1 on the 6, or the 3 now. How many times, excuse me, does 2 go into 8? 4. And then I took an x out. How many x's were on the 8? 1. So if I took it out, does that 4 have an x left? No, it's gone. So this is the factored form for that polynomial. Making a little bit of sense?
I don't understand what is off there.
The x off. Okay, so here we're saying they have 1 x in common. So kind of another way to think about what's left in the parentheses is if I pulled a 2x, you understand that the x is what they have in common, the 2x is a GCF. Okay, so I think this will make more sense to you then. What times 2x would get me 6x squared? I need a 3 and another x to get the x squared. And then I've got a 2x. What times 2x would get me 8x? I just need a 4 because I've already got an x that's on the 2. Does that make a little bit more sense? We're gonna do some more. I think it'll start making a little bit more sense. Yes, sir.
I'm curious what back and forth means. What would
We're going to use it to solve polynomials to get their zeros or where they cross the x-axis, x-intercepts is what it is. Yeah, that's where we're headed. That's where we're headed is to solving them or finding the zeros of polynomials. Let's look at this one. 10 x to the third minus 15 x squared. Is it in descending order? Yes. So we're good there. If it weren't, we just need to rearrange it. Okay, we'll look at one that's not in just a little bit. Okay. Next thing we want to look for is the greatest common factor. 5 goes into 10. 5 goes into 15. What else goes into 10 that's bigger? 10, right? But 10 doesn't go into 15. So that's how you know it's 5. Your GCF, the number can never be bigger than the smallest number that's in the problem. You know, that's always going to be the case. So there's a 5 that comes out. How many x's does the first piece have? 3. The second one has 2. They have in common how many? 2. So that's going to be x squared. Open up a set of parentheses. What times 5x squared would get me 10x to the third? 2 and an x. What times 5x squared would get me 15x squared? We need a minus sign and a 3. Do we need any x's on that? No, because we already got the 2 that go with it out in the front. There's our factored form. We got the x squared out here in the front because this one had 3 and that one had 2. Yeah, we already had the x squared. Absolutely. Yeah, you're right on top. That's it. Okay. Any other questions about this? Because the GCF stuff, I'm kind of trying to spend a little extra time on it because it's the vehicle for doing everything else. So I want to make sure we got it down. Let's do another one of those. Let's say we had x squared plus 9x to the 5th. Is it in descending order? No. So let's rearrange it so that it is. Don't change the sign of anything. So that's a positive 9x squared, or an x to the 5th. So I'm going to put it positive 9x to the 5th in the front. What kind of x squared is this? Positive or negative? Positive. So we're going to put a plus x squared there. Now is it in descending order? Yeah, we don't have an x to the 4th. We don't have an x to the 3rd. We don't have a plain x. But we've got the biggest one first, and then the smallest ones after it. GCF. 1. Yeah, that's right. You wouldn't have to write the 1 in front. You could, but you don't have to unless it's negative. If it's negative, you need to write it there. And we'll look at one where we may need to pull a negative as we get a little further in here. All right. So first one has 5 x's. Second one has 2 x's. Common 2. So just 1x squared. Now here's the tricky part. This is one folks sometimes struggle with, getting the parentheses left on this one. What's the first piece? To the third. I used 2 of the x's outside, so there's 3 left. There were 5 to begin with. If I use 2, there's 3 left. Now, what's the second term?
Plus 1.
Y plus 1. Yeah, so because what times x squared would get me x squared? 1. That's where the 1 is coming from. Technically, guys, don't forget there's a 1 in front of that x squared there. If that helps you to have that there, write it there. No law says you can't. Your textbook never will, but we're smarter than them, right? Or we know what works for us, okay? That's the biggest thing. Now, this one's got an exponent left over inside. We got 9x cubed and 1 there. We would need to check this to see if it's a sum of cubes. I'm saying sum of cubes because it's plus sign. Sum is plus, right? Difference is minus. The key to being a sum of cubes is the number that's involved a cubed number?
Yes.
9 is cubic. What times itself 3 times gives me 9? 3 times 3 is 9. 3 times 3 times 3 is 27. That's what cubed means. So 9 is not a cubic number. 1, yeah, it's cubic, but 9 is not. So that means you can't do it. You can stop right there. We'll get to the sum and difference of cubes in a little bit and talk about how to break those down. But the key is recognizing. I purposely did not have this one do that. That would have been a chain in the spokes of the wheels of life there. Let's do this one. 6x squared y plus 8xy plus 12y. Kind of a fun one. Not too difficult here at the beginning. Now, when there's two variables, it's a little difficult to look at descending order. I wrote this one in descending order the way it should be. Because all we're looking for here is a GCF. That's what I want you to find. 2 goes into 6. 2 goes into 8. 2 goes into 12. I'm looking at the smallest number and thinking, okay, 3 also goes into 6. 3 goes into 12, doesn't it? But does 3 go into 8? No. So that's why 3 is not the GCF. Also think about 6. 6 goes into itself. 6 goes into 12. But does 6 go into 8 evenly? No. So I once I get to the smallest number that's in the problem, then and I've got one that works, I want to pick the biggest one that works. 2 is the biggest one that works. So 2 is the number part of the GCF. What else do all 3 of these have? They all have a y. So they all have a y in common. So that's part of the GCF here is y. Everybody doesn't have an x. The first 2 terms have an x, but the third one does not. So can't do anything with that. Next thing would be, okay, what's left? What x squared? 3x squared plus 4x, yeah, plus just 6. Yeah, no x involved on that one. A little bit more difficult because it got more terms, but you're always going to look for a GCF across all of the terms first. So in descending order, then look for a GCF. There won't always be one. Keep that in mind. There's not always a GCF. These examples had one because we needed to practice GCF. There's not always a GCF. We're about to see some that don't as we start progressing through the other methods for factoring. Okay. All right. Let's start using that GCF idea to factor some larger polynomials that have more terms in them. So still the instructions are still factor the polynomial. That's the name of the game. Let's do this one. X squared plus 6x plus 3x plus 18. And yes, I know it looks like you should simplify it. Don't. Not on this one. Now, when it's presented to me like that, I still go through the chain of command. I say, okay, is it in descending order? I got x squared first, and then I got a plane x, and then I got another plane x. Does it matter what order they're in? No. They're in the middle there. That's where there should be. And then I got something that doesn't have an x. So I'm good. I've got it in descending order. One thing that I'll go ahead and tell you, it really does not matter what order the middle terms are in. And we'll talk about that as we get to trinomials and things, but really doesn't matter. Okay, now, the next step after you do that is GCF. We look at all four terms. And is there a GCF between x squared, 6x, 3x, and 18? Just one. So that's one of those cases where really there's not a GCF that helps us any. Pulling a 1 out doesn't change anything, right? So I divide everybody by 1, I get the same thing back. So nothing to do there for GCF. The next thing to look at is how many terms do we have? Terms are separated by addition or subtraction. There's 1, 2, 3, 4 terms. Grouping is the method that we want to do there, okay? So if it's got 4 terms, we're going to group. And the way you group is you put the first 2 together and the last 2 together. So I'm gonna group the first 2, and we're going to work that part first. Once I've grouped the first 2 together, I look at, it's going to go black. Ran over my cord here. I'm going to look at those 2 terms, and I'm going to think GCF of those 2 terms. Is there a GCF between those 2? 1 and x. So there is something that I can pull out. So I'm going to pull an x out of those 2 terms only. Okay? X to the front. What would be left in the parentheses? X plus 6. Okay, then I'm going to look at the second 2, and I always underline them so I don't lose it. A lot of times folks will want to put them both in parentheses, and they'll put their parentheses right through that sign, and it messes them up because they'll forget if it's a positive or a negative. So I just underline the second group. And I think, okay, is there GCF between these 2? 3. 3 goes into itself, 3 goes into 18. Okay, so I'm going to pull a 3 out. The sign that's right there keeps going down the middle. So I'm going to put a positive 3 out in the front. What's left in the parentheses? Do you think it's a coincidence that those parentheses match? I'm a math guy. There's no coincidences in math. I'm also, my faith says there's no such thing as a coincidence either, but those things matching is the key. If they don't match, something's not right. It either doesn't factor or you didn't pull out the GCF. Okay, so if those match, hey, that's good. Now here's the ticket to the end of this problem. The factored form, the matching piece comes out to the front, and then the stuff that's out in front of those. That's where that's coming from. X plus 6, that's the matching piece. The things that are in front of those 2 is the other factor. Okay? The matching piece is one factor. Stuff in front is the other factor. And we factored a polynomial that had 4 terms in it by grouping. Trust me, we're going to do some more. I'm only going to give you one example of this. So there's our factored form. If you multiplied this problem back out, x times x is x squared, x times 3 is 3x, 6 times x is 6x, 6 times 3 is 18. We get the original problem back if we multiplied it out with distributive property like we were doing in R.3. That's one thing you can always check yourself to see, okay, if I multiply this back out, do I get the same thing back that I started with? If I don't, something went wrong, either in your factoring or in your multiplying. Okay. Let's look at this one. 4x to the third plus 2x squared minus 2x minus 1. Excuse me. Is that one in descending order? Got x cubed, x squared, plain x, no x's. That's descending order. Is there a GCF across the entire problem? Just one. 4, 2, and 2 have something in common, but this one hanging on the end screws it up. There's always that guy. So, no GCF. How many terms are there? 4. So we do what? Group. First two together. What's the GCF of 4x cubed and 2x squared? 2x squared. Good job. 2 goes into both of them. One's got 3 x's. The other one's got 2. They can pair up 2 of them. So that's where the x squared comes from. What would be left in the parentheses? 2x plus 1. Uh-oh. That's positive in there. My next group has negatives. Huh. What's the GCF of negative 2x and negative 1? Negative 1. Why are we pulling a negative? What will it do? It's the middle sign. It's always going to come down. That's true. What does dividing negative 2x by negative 1 do? Makes it positive. What does dividing negative 1 by negative 1 do? Makes it positive 1. So that's the actual math that's happening. If you'll keep in mind, if you're doing grouping, that middle sign should always carry down. That'll tell you whether or not you need to pull out a negative. Is by this middle sign. If that third term is negative, then your GCF of your second group better be negative. If that third term is positive, your GCF of your second group should be positive.
So if it was negative 2x minus 2, the GCF would be negative 2, right?
Mm-hmm. Yes. It wouldn't work for this one if that was the case, but yeah. Yeah, that's exactly the right idea. Now, do the parentheses match? Yes. So that means we did that it factored. And it factored as 2x plus 1. And then the other factor is 2x squared minus 1. The matching parentheses is one factor. The other factor is the stuff that's in front. Well, let's do another. 10x to the third minus 6x squared plus 25x minus 15. All right. Over the whole problem?
No, just for the first two.
Oh, it's the first group. Okay, so there's no GCF for the entire problem. 10, 6, 25, and 15. The 6 messes that up. We thought maybe 5 would work, but 6 messes it up. So, yeah, if we group the first two together, the GCF for those two would be 2x squared. And that would leave what in the parentheses? 5x minus 3. What times 2x squared would give us 10x to the third, 5, and an x? What times 2x squared would give us negative 6, negative 3? Second group. What kind of 5? Positive or negative? Positive 5. What's that leave in the parentheses? Minus 3. Parentheses match, don't they? Hey, that means things are working right. The world is spinning at the correct angle and the proper speed to lead us to tomorrow. 2x plus 5, 5x minus 3. Notice I wrote that in a different order than what I've been writing it. Does it matter? Why not? Yeah, it's exactly right. That multiplication is commutative. It doesn't matter what order you write it in. Now, the stuff inside of the factors matters, what order you write that in. But if you wrote 5x minus 3 parentheses and then 2x plus 5 in parentheses second, it's the same answer. Okay, so understand that you can write them in any order you want to there as far as which factor comes first or second. So grouping is going okay. Let's hit a speed bump here. Oops, not 17. Make that a 12. 17 won't work. X squared plus 7x plus 12. That doesn't have 4 terms in it. That stinks. That means I can't use grouping anymore. I got to use the X method. Okay, I'm going to show you how to do the X method. The X method is stemmed off of knowing quadratic form. Quadratic form is ax squared plus bx plus c. That's the form. Commit that to memory. We're going to use that a lot in the next 3 weeks. Probably you still use it a lot between now and December the 11th. You will still use that a lot after January when we're doing Math 110. Okay, so that's something we're just going to need to know. Okay, now the way the X method works, you make a big X. X method. All right. The number that goes in the top portion of the X is found by taking A times C. Okay. For our problem, what's in front of X squared? 1. So we're saying 1 times 12. So a 12 goes up here. The bottom number of the X, down here in the bottom part, is B. What's B in our particular problem? 7. Okay? Let me write that for you. Okay? Now, what we need to find to go in these blanks on the side, we need 2 numbers that multiply to be 12 and add to be 7. So what you need, instead of guessing what numbers could work here, you're saying, okay, I only can use the numbers that multiply to be 12. So that narrows it down to either 1 times 12. What's 1 times 12? 12. What's 1 plus 12? 13, not 7. So that one's out. 6 times 2. That multiplies to be 12. What's 6 plus 2? Almost. Not quite. Okay? What else multiplies to be 12? 3 times 4. 3 times 4 is 12. 3 plus 4 is 7. So that's the 2 numbers that we want to use. Okay? So we're using 3 and 4. Absolutely not. Doesn't matter what order. And this kind of goes back to that first example of grouping that we did, and I told you it didn't matter what order it goes in. Okay? So now here's the trick to doing this, and we're going to learn some shortcuts later on for this. The trick is, what you're doing is taking a 3-termed polynomial, turning it into a 4-termed polynomial so that you can do grouping, because you already know how to do grouping. So if I replace the 7x with 3 and 4, I can now do grouping. 3x plus 4x is 7, right? That was the same thing. But we've just we've manipulated the problem so that we can do what we want with it. Okay? It's kind of like a con game. You kind of manipulate your customer so you can do what you want with their money and time. So that helps you remember it. Okay. So x squared plus 3x, what's the GCF of those two? What's that leave in parentheses? GCF of 4x and 12. Yeah, 4 goes into itself, 4 goes into 12. That's the biggest one. 2 would also be a common factor, but it's not the biggest one. So we're going to use 4. What's that leave in parentheses? What do you know? What do you know? They match. That means x plus 3, x plus 4 is the factored form for that trinomial that we started, that 3-termed polynomial, trinomial that we started with. Now, here's the shortcut. When there's, what was in front of x squared? 1. When it's 1 in front of the x squared, look at our numbers in our x. Positive 3 and positive 4. Plus 3 and plus 4. That's always going to work that way. We'll do some more examples. You'll see that it's always going to do that. You can do the grouping every time. It's the long way. There is a shortcut, but it only happens when there's a 1 in front of the x squared. If there's anything else there, you can't do it. Only if there's a 1 in front of x squared can you do the shortcut and go straight from here to those. Okay. We'll see some examples as we go here. Four x squared minus 11x plus 6. Is it in descending order? Is there a GCF for the entire problem? No. So we go to count terms. How many terms? 3. So it's X method. What number goes in the top of this X? 4 times 6, which is 24. That's where that's coming from. It's 4 times 6. A times C. The number in front of x squared times the plain number that's on the end. That's what you're going to use every time to do that. Okay? What number goes in the bottom? Negative 11. Be careful of that. That sign has got to go with it. You treat it, whatever sign is with it, you take it with you. Now, so we're needing two numbers that multiply to be a positive 24, but add to be a negative number. What do we know about two numbers that multiply together to be a positive and then add to be a negative? What do we know about them? They're both going to be negative. So we need to just think about, what are the factors of 24 that might work here? Negative 3 times negative 8? Absolutely. That is the right two numbers. Okay? Negative 3, negative 8. If you wrote negative 8 first, it doesn't matter. Why would negative 4 and negative 6 not work? Because it doesn't add up to be negative 11. That's the key. You've got to have factors of 24. That narrows it down to either 1 and 24, 2 and 12, 4 and 6, 3 and 8. That's it. I've got them all. You got to think about what multiply. If you know your multiplication tables, factoring is a lot easier. It's not impossible if you don't know them well. Okay? You just got to, it just may take you a little longer to get to the right two numbers. Okay? So it's possible. If you don't know your multiplication tables well, you can still factor. It's just going to take you a little bit longer to get that number. All right. So what do I do with the negative 3 and the negative 8? Replace the middle. Doesn't matter what order I put them in there. No. Which one do you think you'd want to pair with the 4? The 8. That's how I think about it. When I go to do this, I'm going to put the minus 8x there and then the minus 3x here. Because it makes sense to me to have the 4 and the 8 together and the 3 and the 6 together. Because I know I'm going to do GCF in a minute. So putting things that I already know go together really can shorten up my work. I don't have to think so hard. GCF of the first group. 4x. Leaving x minus 2. Yeah, be careful on that. Pretty common mistake to forget to divide and subtract instead. What do I need to pull out of the second pair? What kind of 3? Negative 3. What's that leave in parentheses? X minus 2. Positive 6 divided by negative 3 is negative 2. That's where that sign is changing. Anytime that's a negative right there in the middle, it's going to change the sign when you pull out the GCF. It'll change the sign of the stuff inside. It's always going to swap that. Okay? What's the factored form? Notice that my factors here at the end didn't match my numbers on the side of my x because of the 4 in front of the x squared. That's what made that happen. If that had a 1 in front of x squared, they will match. Because it's got something else, they don't match. Okay. It should have been an X, sorry. Got bored there with the same letter. I guess my brain said, throw it in. All right. What do we do? X method. All right. So what goes up top? Try again. Negative 30. What goes on the bottom? All right. So multiplying to be a negative number and adding to be a negative number. What do we know about our two numbers? They're not both negative. One's negative. Which one? The bigger one or the smaller one? The bigger one. All right. So that's if the number up top is negative, you know that your side numbers are going to be opposite signs. One's positive, one negative. This tells you the sign of the biggest one. If it's a negative down here, the bigger one will be negative. If it's positive down here, then the bigger one will be positive. So there's just some short clues that kind of can help speed you up. They're not necessarily shortcuts in any way, but they can help speed you up. So we got to think about things that multiply to be 30. There's more options when you got a bigger number up there. So what things multiply to be 30? No fractions. Definitely no fractions involved. 3 and 10 is one of the easiest ways to multiply to be 30. And 3 and 10 are how many numbers apart? They're 7. All we got to do is get the sign right. Which one should be negative? The 10, because it's bigger, right? So it's negative 10, positive 3. And it's kind of, you just go through the factors of 30 and get the ones that are right distance apart. 2 and 15, it multiplies to be 30, but they're 13 apart. It's too much. So you got to get some numbers that because the bottom number was negative. You've always got to, you don't even have to think about that. You can actually just say, okay, what's negative 10 plus 3? It's negative 7. That's the right thing. If you'd had the negative on the 3, positive 10 plus negative 3 is positive 7, not the right number. So you don't overthink that part. It just kind of can help you sometimes on the tougher ones to get the right sign. But just always check. Add them together. If it doesn't get you the right number, swap the signs. Add them together again. It gets you the right number, good. If it doesn't, then those are not the right two numbers. Go for something else. That's kind of, I told you it's not guess and check. It's not because you've narrowed down the number of choices, but it is still kind of, you pick one and try it. If it doesn't work, go to the next one. If it doesn't work, go to the next one. That sort of thing. Okay. All right. So then we take the 10 and the 3 and replace the negative 7x with it. I'm going to put the 3 with the 6. Does that make sense, right? If you put the 10 with the 6, it doesn't screw it up. It'll get the same factors at the end. It'll look a little different, but it'll get you the same factors. So if I did it this way, I'm going to do it both ways to show you that it doesn't matter what order you put the middle terms in. If I group the first two together on the left, what's the GCF of 6x squared and 3x? 3x. What's it leave in parentheses? 2x plus 1. Good. What do I pull out of the second pair? That leaves the same thing, 2x plus 1. My final factors, 2x plus 1, 3x minus 5. Over here, if I group the first two together, what's the GCF of 6x squared and negative 10x? 2x. What's that leave in parentheses? Minus 5, right? What do 3x and negative 5 have in common? Just 1. Pull the 1 out, it doesn't change it, right? Same factors. I got 3x minus 5 and 2x plus 1. I get the same thing. That middle step looks a lot different because it's got a different matching parenthesis, but it's still the same x. So it doesn't matter what order you put the middle part in for, it's still there. All right. Let's do this one. If you can do this, x squared plus 5x minus 14. Definitely sticking to the x method here. Negative 14, add to be 5. Multiply to be negative 14, add to be positive 5. Seven and negative 2. Positive 7, negative 2. I like it. Can I take a shortcut on this one? Yeah. There's a 1 in front of x squared. So I could go straight to my factors. X plus 7, x minus 2. That's a good cheat code for whatever. I don't know if they do. Did they do cheat codes anymore? I haven't played video games in years. Oh, okay. You pay for Bitcoin to get to the next level. Okay. All right. So if you don't do the shortcut, it still works, guys. You can still go x squared plus 7x minus 2x minus 14 and group. And then those we pull out a negative 2 and get the same thing. So if the shortcut kind of blows your mind, just group. It's going to work. The shortcut's nice. It only works, though, when there's a 1 in front. That happens a good fair bit of the time, so it's not anything uncommon for you to get that 1 there. Oh, I'm not. I'm just going to go right underneath it and write the next thing we're going to do. As I told you, this section is the longest one, just because I try to make sure I'm giving you plenty of examples and explanations on the ways of factoring, because it's an important skill. Can't convince my Algebra 2 class of that, but it is an important skill. All right. A little different problem here. Example M. X squared minus 4. Is that in descending order? Okay. Is there a GCF? 1, so nothing really. Okay. How many terms? 2. Okay, so there's only 2 terms, and my rules of factoring says that's either a difference of squares or a sum or difference of cubes. Look at the exponent on the variable. It's a squares. There's a minus sign in the middle, so that tells me, oh, this may be a difference of squares. It doesn't always guarantee it is, but it may be. So what we need to do then is try to write it as a difference of squares. If I can rewrite it to fit this pattern. something squared minus something else squared. What squared gives me x squared? X, right? Just, it is that simple. Don't overthink that part. What squared would give me 4? 2. So I can rewrite that as squared minus a squared. So that means it is a difference of squares. The factors for a difference of squares x plus 2, x minus 2 in this case. Whatever's squared in the front goes in the front of each factor. Whatever's squared in the back goes in the back of each factor. One's a plus, one's a minus. This also works with the x method, even though it doesn't have 3 terms. You just put a 0 in the bottom, and you can do the x method with it. I don't think that makes it very easy. I think that recognizing this is the best thing. Remember when we did problems like this in R.3 just a little bit ago? What happened to the middle term? It was positive 2x and negative 2x. They canceled out. That's how you ended up with the 2-termed polynomial. Right beside that, let's do this next one. Let's say we had 16x squared minus 25. A little bit more difficult one, but seeing the pattern here can make it easier. Is there a GCF between 16 and 25? No. Not a variable in common, so nothing there. It's got 2 terms. The variable has an x squared on it. So that tells me, okay, it's probably a difference of squares. It's a minus sign in the middle. If it has a plus sign in the middle, it can't be a difference of squares because difference is always minus. Okay, so what squared gets me 16x squared? Okay, all right. 4 and an x, yeah. What squared would get us 25? 5. Open up 2 factors. What's in the front of both of them? 4x. What's in the back of both of them? 5. One's a plus, one's a minus. It doesn't matter which one you make the plus and which one you make the minus. I have a I don't know if you'd call it a condition where I have to do things the same way all the time. But that's the way I've always done it. So I always just put the plus first. It doesn't matter. Some people put the minus first so they don't forget it because it's the different one.
The sum, would they both just be plus 5?
Mm-mm. Sums don't factor. Sums of squares don't factor. Only differences of squares. Cubes will, and we'll see that in just a couple of examples away. The donut example. $25 x to the 4th minus 144. Yeah, curveball. $25 and 144. They have a GCF. 2 terms with a minus sign in the middle, but that x doesn't have a squared on it. It's got a 4th power. It doesn't have a cubed for sure. So I'm thinking, okay, it's an even exponent. It possibly could be a squares. So I'm going to try to rewrite it as a squares. Just because if it will rewrite this way, I think I can factor it. 144. What squared gets me 144? 12. That's the easy part. The first part's a little more difficult. What squared gets me 25? 5. And then what squared gets me x to the 4th? X squared. Yeah, it takes 2 x's times another 2 x's to get an x to the 4th. That's written as a difference of squares. So that means it factors. What's in the front of both factors? What's in the back? One's plus, one's minus. So we factored something that was a little bit bigger than an x squared, but it fit the pattern. And that's the key to differences of squares. Is it fits the pattern, then it'll factor that way. You won't see a whole lot in this course, especially in this particular section and Canvas quiz and test that goes above x squared. A few, but not many, especially with the differences of squares and stuff. All right, let's look at that other two-termed monster, the sum and difference of cubes. Okay, I told you it's a memorized pattern. It really is. The sum of cubes. Let's say we had x and y for lack of anything else. We'll do some examples with numbers in there. If we could rewrite it as something cubed plus something else cubed, we can rewrite it like that, similar to the way we did differences of squares. Then we can use this pattern to help us factor it. There's a short piece and a long piece. That's what you got to remember. The short piece is the same, meaning that it's got the same sign in it. It's a plus. And then it's the same pieces, x and y. So it's x plus y for the short one in this case. The long piece, I like to think of as the leftovers. Okay? In the short piece, I used one x. That means there's how many left? 2 left over. So there's an x squared. I used one y. So there's how many left over? 2. So there's y squared left over. That's on the end. But then there's this middle piece that we forget about. The middle piece, it has the opposite sign. So if it's a sum of cubes, it'll be a minus sign in the middle of the long piece. And then you just multiply them together, x, y. And there's the factored form for a sum of cubes. We're going to do some examples with numbers in there and look at that. But that pattern is something you need to memorize. If you use a difference of cubes, the short piece is the same, so it's x minus y. The long piece, square the front, square the back, plus sign, and then x, y in the middle. Really, you just have to memorize that pattern to remember how to factor sums and differences of cubes. I don't have a catchy way of doing that. Not a song that goes with it, or dance, or something like that. But memorizing that is the key. Okay. All right. Let's look at an example with some numbers involved, so that we can put that to practice. Okay. We'll come up with the dance for next week. Yeah, me too. Make it go viral. All right. It's got a minus sign in the middle. It's got 2 terms. My first stop would be differences of squares, but because it has x cubed, I know it can't be a difference of squares. So it has to be a difference of cubes, possibly. Doesn't mean it is, but it could be. So we're going to try to rewrite it as a difference of cubes. What cubed gets me x cubed? X. What cubed gets me 8? 2. 2 times 2 times 2 is 8. So it is a difference of cubes. So that means the factors are going to follow this pattern. X minus what? What would go here? 2 in this case. So the short piece, x minus 2. Now the long piece. What goes in the front of the long piece? X squared. Insert some space so I can scroll up. So I'm down to the bottom of the screen so you can't see as well. What goes in the back? Plus 2 squared. I'm going to write what you said because that's where that's coming from. And then the middle, it's going to be plus x times 2, which is 2x. When we kind of simplify a little bit here, the x minus 2, x squared plus 2x. What's 2 squared? 4. That's the factored form for that. A difference of cubes. If it's a sum or difference of cubes, they're not going to get big numbers on you guys because, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. The numbers are going up pretty fast. When you cube something, the numbers climb quickly. 5 cubes, 125. 6 cubes, 216. I lost it after that. I don't know what 7 cubed is. 343, actually. Maybe. Yeah. 8 cubed, 1,024. Half 1,024. Sorry. Yeah, I forget those. I don't have them memorized that high. I don't have a need for it anymore.
Does it have to be
As,
plus 4, or could it be 2 squared?
no, go ahead and simplify that number that's there. Go ahead and multiply it out. Think about it. Okay, and if you left the blue step out and didn't even write that, that's fine with me. I mean, but go ahead and simplify that number. That's a key thing there. Let's do one that's got maybe a number in the front there. Uh, 64x to the third plus 27. So I'm thinking, okay, it's got a cubed, it's got a plus sign. Maybe it's a sum of cubes. I know 27 is 3. I know 64 is 4 and an x. So I've rewritten it as a sum of cubes. Okay. Short piece. 4x plus 3. That's the easy part. Most people can get that part. But where most people mess up is a sign or not simplifying on the long piece. Okay. So the long piece, yeah, it's 4x squared. You're squaring 4 and you're squaring x. Okay. And then on the end, we got 3 squared, right? What's in the middle? 3 times 4. 12x. Again, that's coming from saying 4x times 3. That's where this is coming from. Multiplying the two pieces that made the sum of cubes together. Then simplify that long piece. That'd be 16x squared minus 12x plus 9 and 4x plus 3. The long piece, even though it has 3 terms, you would think you could do X method to factor it. Because it came from a sum or a difference of cubes, it will never factor any further. So that's kind of a nicety of sums and differences of cubes. They're tough. You got to memorize a pattern, but you get the benefit of the long piece never changes. It doesn't factor any further. We're going to see some in just a minute where we're actually having to factor another time after we get something else done. So there's a sum of cubes. Memorize the pattern. There's really no better way to do it than that, than memorizing that pattern. All right, let's get 5x squared minus 20. Let's kind of put some of this stuff together that we've done. We've kind of separated it and kind of compartmentalized the things that we're doing. Let's put it together and be able to do it all at once. So this is where you go through your rules all the way again. Okay, so descending order, GCF, 5. So we pull a 5 out. What's left? Minus 4. Will that factor any further? Looks like it might be a difference of squares, right? Because it's got x squared, a minus sign, and then a number. So I'm just trying to see if I can rewrite it that way. That was x. What squared is 4? 2. So the 5 is already out there. What are the two factors that come from x squared minus 4? Yeah, x minus 2 and x plus 2. There is the factored form. We could factor that other piece a little further after we did the GCF. X to the second minus 80x plus 160. What do you do first? It's in order. The GCF is 10, so we're going to pull that out. What's that leave in parentheses? Excuse me. 16. Okay. Then we look at what's left in the parentheses, and we try to decide, can we factor it further? What method would we need to use on the stuff left in parentheses? How many terms are in these parentheses? There's 3, so that's the X method. The 10 is not part of the problem anymore. Okay, it's just hanging out. Okay, it's the Christmas tree hanging on the rear view. It doesn't do anything once the smell goes away. Okay, it's just riding along, watching what's happening. So we're looking at what's in front of x squared here. 1. 1 times 16 gives me the 16 that goes in the top. Negative 8 goes in the bottom. What multiplies to be a positive 16 and adds to be a negative 8? 4 times negative 4 times negative 4. Can I take a shortcut on this part? Why? The x squared is not got anything in front. It's got a 1 in front of it. Doesn't have any other number in there. So I could go straight to my factors. X minus 4 and x minus 4. The 10 still comes down. So this is correct. Or you could write it x minus 4 squared like that. Both of those are correct factored forms of that. Pulling a GCF and then using the X method on what's left over. X cubed minus 5x squared minus 4x plus 20. Grouping. GCF of first group. Leaving x minus 5 inside. GCF the second group. minus 4. Leaves x minus 5. So our factors are x minus 5 and x squared minus 4. Will one of those factor any further? Yeah, we've done it a couple of times already tonight. We know that it factors as the difference of squares as x plus 2, x minus 2. The x minus 5 just comes down with it. That x squared minus 4 is that difference of squares, x squared minus 2 squared. That's how we're factoring that as x plus 2 and x minus 2. So it's mixing in what we've done, just kind of mixing it all together here, trying to get it, what's going on there. X squared plus 9x minus 13. Okay, I could try to use the x method here because it's got 3 terms. Negative 13 had to be 9. Negative 13 and positive 1. That doesn't work. What about positive 13 and negative 1? That doesn't work either. Are there any other numbers that multiply to be 13 that are not fractions? No. That means that won't factor. That's called prime. Yeah. Well, those are, you call them your favorite kind, but sometimes they're the most frustrating because, maybe they got like a 20 and it's got to add to be, 7. And you've got to try all the factors of 20. Or maybe it's a number like 48 has a lot more factors in it. So you got a lot of things to try. And if you forget one, you could possibly miss it if you forget one of those. So if it will not factor at all, then it's called prime. Or you can write cannot be factored. That means the same thing. Okay. All right. So there's factoring. Finally, finished with that section. A lot of stuff in that section. We got 2 short sections here, though, to finish off the night. Do you guys need a break, or you want to just push through? You've got 30 minutes. I think I can get them both in 30 minutes, get you out of here by 8. I'm good. I'm good for it if you are. Without rushing, I can get through that. So, square. It's videoing right now. Square roots. You might also hear me say the word radical. Radicals. Square roots, radicals mean the same thing. Okay. All right. So we're going to be working on simplifying radicals or square roots. Okay. We'll start with something easy. The square root of 9. Why? 3 times 3 is 9. There's a pair of 3's there. If we're dealing with square roots, we look for pairs. A pair of 3's is represented by that 3 that's on the outside, not inside a radical. That's why the square root of 9 is 3. The square root of 16. The y, what multiplies to be 16? Besides 4 and 4. Don't use 4 and 4. 2 and 8. And 8 breaks down to 4 and 2. Here's what we have. 1, 2 pairs of 2's. 4 is 2 times 2, right? So we're finding pairs there. What we're building up to is the fact that you're not going to get perfect square numbers every time. So this factor tree is a really good method for simplifying radicals or square roots. Not getting decimal answers, but getting simplified radicals. For example, if we wanted to simplify the square root of 18, I could pull out the calculator, and type in the square root of 18. and I get a nice ugly decimal. That's not what I want. I want the exact value. Okay, the exact value can be found by doing a factor tree for 18. Factor trees are kind of elementary school stuff that you hadn't done probably in a while. The way you want to do a factor tree is you just think of two numbers that multiply to be 18. It doesn't matter if one of them is a square number or not. When I think of 18, the first one I always think about is 6 and 3. I don't know why. 9 and 2 also works. It doesn't matter what two numbers you start with as long as they multiply to be the number above them. Okay, so if I use 6 and 3, I'll look at those two numbers and say, okay, well, either of those break down. 6 is 2 times 3. Why will 3 not break down? Yeah, it's only one in itself. It's a prime number. So you want to break those numbers down until everybody at the end of the branch is a prime number. And then you look for pairs, sets of 2. Okay? There's one set of 2 3s. So what that means is 1 3 comes to the outside. And this 2 that doesn't have a buddy, he stays in the house. Anybody that's a pair goes to the outside. Anybody that doesn't have a pair stays on the inside. Say it again. That's right. If you ain't got a buddy, you can't get out of the house. So let's work on 24. So a factor tree for 24, what could we start with? 8 times 3. We could have started with 12 and 2. 6 and 4. Doesn't matter which one, just as long as that multiplies to be 24. Then which one of those will break down? 8. 8 breaks down to 4 times 2. 4 breaks down to 2 times 2. How many pairs do I have? Just one pair of 2s. If I pick those 2, that's fine. If you didn't pick those 2 that were side by side and you picked those 2, it's the same thing. It doesn't matter which pair of 2s you picked. Just you're picking a pair of 2s. So that means that there's only one 2 that comes to the outside. This 2 and this 3 are both left on the inside, and you multiply them back together. So it ends up being 2 radical 6. 2 square root of 6 is what the simplified version of square root of 24 is. The good thing about the factor tree method is when you start doing like cube roots later on, like Math 110, we'll do some stuff with cube roots. You look for sets of 3. Fourth root, you look for sets of 4. Fifth root, you look for sets of 5. You just don't get very much bigger than that, any bigger than that. But you're just looking for whatever. If you're doing a square root, you're looking for a set of 2, and it's real simple that way. Let's do E. Let's do 108. What multiplies to be 108? 54 times 2, that works. Could have used 9 and 12. Would also be an option. 27 and, no, not 27. 36 and 3. But 54 and 2 works. 54 breaks down to, once you get it down to the prime ends of the branches, they all have the same numbers there, no matter which ones you started with. 54 is 27 and 2. 27, 3 and 9. 9 is 3 and 3. Then you look for pairs. Got a pair of 2s. Got a pair of 3s. I only have one end of a branch that's not got a buddy. The 3. 2 on the outside, 3 on the outside, 1 3 left on the inside. you multiply the 2 and the 3 together on the outside. 6 radical 3. Negative square root of 300.
That means 300 is negative.
Means the answer will be negative. That's all that means. We'll get to, in the next section, we'll talk about what happens if the negative's on the inside with the 300. We'll work. 75 times how much? I'm gonna do 3 and 100. That's easier. 10 and 10. 5 and 2. You'll get to the same place. 3 and 100 works. 25. You can think about quarters and $3. How many quarters and $3? 5 and 12. But look at our pairs. Pair of 5s. Pair of 2s. This 3 doesn't have a buddy. So it's a negative, 2, a 5, 3 left on the inside, so that's negative 10. Radical 3. The negative is just carried over from the front. That's where it was there to begin with. You just carry it with you. Know that it's just going to be a negative at the end. Let's see. What are we on? G. Let's throw a fraction in there. We're not real hard on you with the fractions in this particular section. Way to think about them is just say, oh, what's the square root of 16? What's the square root of 25? What is the square root of 16? 4. Square root of 25. And that's the fraction. Like I said, we're not. The first time I taught this course, they were pretty tough on you with the fractions, and come to find out, it really didn't help you any later on in the course to have the really hard fraction stuff. So they took it out, and I was proud of them. So square root of 144, square root of 49. Try again. 7. Leave it as the improper fraction. Reduce if possible, but just leave it improper. All right, let's look at a little bit of operation stuff with these. If we had the square root of 6 times the square root of 12. Anytime you're multiplying radicals, the rule is inside times inside, outside times outside. On this one, we don't have anything on the outside, so we don't have to worry about that. We just do inside times inside. 6 times 12 is 72, right? And then we simplify that. I got it from 6 and 12. 3 and 2, 3 and 4. There's a pair of 2s. There's a pair of 3s. 2 times 3. Radical 2. 6 radical 2. Inside times inside. Outside times outside. Simplify last. The reason you want to simplify last and not first when you're multiplying is because if you simplify first, you're probably going to have to simplify again after you've multiplied because the number inside is going to get bigger. So just wait and do it at the end. Let's do one that's got numbers on the outside. 3 radical 8 times negative 5 radical 12. Make it fun. $96. And break down the 96. 12, 4 and 2, 2 and 2, 2 and 6, 3 and 2. Pairs, 2 pairs of 2s. I still have the negative 15 out there. And then I put the 2 2s. And then what's left on the inside? This 3 and this 2. So that'd be negative 15 times 2 is negative 30 times 2 is negative 60. Radical 6. There's something already out there. It just kind of hangs out and then multiplies to anything else that comes out. All right. Not too bad. Easy stuff. All right. Last section of the night. Yeehaw! What have we been looking for? 1.3. So we skip out of the R chapter into chapter 1 and go all the way to section 3. And we talk about what's called complex numbers. It is not really complex. The complex number system is where imaginary numbers come from. Imaginary numbers was a really unfortunate naming accident in mathematical history. There were these two guys that were pen pals because Twitter didn't exist and Snapchat hadn't been invented yet. Back in the, I want to think it was around 1400, something like that. They were challenging each other in mathematical abilities. They were both really good, and they were coming up with new ideas around the same time, and they knew about it. They had met at some other really smart person's house, and so they got to writing letters back and forth to each other and challenging each other with different equations to solve. And what they found out was, okay, if the equation had x to the 4th power in it, then that meant it had 4 answers. Well, they didn't have the abilities yet to find all 4 of them. They could find 2 of them. They knew there should be 4 because every one of them that they could solve had all 4 of them. But then there were some of these polynomials that you could only find 2, and there were 2 that were supposed to be there, and they couldn't find them. So they started calling them imaginary solutions, but because they didn't know what else to call them, they didn't know what to do. Well, later on in math history, they figured out, oh, this is how you find those, and the imaginary part stuck. So imaginary numbers, complex numbers, same idea. They're in the same family there. But imaginary is not really a good term because that means it doesn't exist, like unicorns. Do they? Okay. All right. So imaginary, it's just the unfortunate naming accident. I got taken away from the world of variables and said, okay, we're going to define I means this. I means the square root of -1. So this is the key that kept those two guys from finding those solutions that they knew existed. They just didn't know how to get it. It was the fact that I, representing the square root of -1, could give them some stuff. And if you have I squared, if I square the square root of -1, I get -1. And if I do I to the 3rd power, that'd be -I. And then I to the 4th power is +1. That little chart right there, you need to log that thing in the memory bank, okay? Because it's going to be helpful when we do some stuff throughout the next month or so, okay? So log that little thing in the memory bank. We're going to need it, okay? After the 4th power, when you get to I to the 5th, it just starts cycling back through. So I to the 5th is the same as I. I to the 6th is the same as I squared. I to the 7th is the same as I to the 3rd. I to the 8th is the same as I to the 4th. It just cycles back over and over and over. If you're familiar with modulo numbers, that's what that is. But you don't have to be familiar with it to know it cycles. All right. Now, a complex number is written in this fashion. A plus BI. This is the real part. This is what's called the imaginary part. Okay. The A, the number in front there, that doesn't have the I is the real portion. The imaginary portion is the part with the I. Together, they make a complex number. Has a real portion and an imaginary portion. That makes it complex. That's what the complex number system does. Okay. Now, where the complex numbers come in is when we go back to simplifying radicals. If that number inside of the radical or square root is a negative, then we have the I involved, the imaginary part. Okay, so let's start there with some simplifying of some radicals that have some negatives. Some we've seen so far. The square root of negative 24. You do the number part just like we just got through doing. Do the factor tree for 24, 12 and 2, 6 and 2, excuse me, 3 and 2. Pair of 2s. 2 radical 6. But because it was negative on the inside, you put an I out there with that 2. That I is because of that negative. That's what made that happen. The negative on the inside makes the I appear on the outside. Eight? No, it wouldn't be 4 and 4. It'd be 4 and 2. 8 times 3. And then you'd have a pair of 2s and still a 3 and a 2. That no matter which ones you start with, you still end up with the same ends of your branches. And then because it was a negative, the I came out. And then we do the number the same way. Say we had like negative 72. Breaking down 72, you can do 6 and 12, 6 and 2, 3 and 2, 3 and 2. We have a pair of 3s, a pair of 2s, 1, 2 left over. So what's on the outside? 6I. Where'd the I come from again? The negative that was on the inside made the I appear on the outside. That 2 is the leftover inside. Common mistake when you're simplifying radicals is to go up here and grab that 12 and put it on the inside. That's a very common mistake that I see a lot at every level. That's all right. Yes, that's exactly right. Yes, you're on the right track. What about the square root of negative 35? What multiplies by 35? 5 and 7, did they break down any further? No. Do we have any pairs? No. So nothing comes out for the 35. Just an I for the negative, and then radical 35. So it would simplify a little bit. The I came out, but the 35 didn't break down any to have pairs. So we leave the 35 on the inside. All right. Simplifying radicals. Throw the negative in the inside. The I comes out every time. All right. Now, let's do a little bit of multiplication with these. Here's a kind of seems like counterintuitive because I'm going to tell you to simplify first when I just told you to simplify last earlier. Now, the part you simplify first is the negative. Number-wise, you still don't do that until the end. 7 and 7 be 49.
49.
That's the number that's on the inside. But if you did -7 times -7, you get positive 49. But we lose the complex part of the thing. This is actually I radical 7. This is actually I radical 7. So when I multiply it, I get I squared radical 49. What's the square root of 49? 7. What's I squared? -1. So I really get -7. Not 7 like I would have gotten if I multiplied before I got the I out. -12 under a radical times a -15 under a radical. Now, the reason that you pull the I out first is because in order of operations, it's supposed to be parentheses first. There's no parentheses in here. Then it's exponents. Square roots are really exponents. Okay, that's why you got to kind of work with those before you do your multiplication and division, because that's the next step after exponents, right? So that's why we need to pull that I out. We can get away with not simplifying the number because we're going to simplify it again anyway at the end. So we're kind of taking a shortcut and saying, okay, instead of simplifying 3 or 4 times, I'm just going to do it once at the end with the number. But I have to take the I out to the front first. So I really have I radical 12 times I radical 15, and then multiply that together to get I squared. I don't even know what 12 times 15 is. It doesn't matter because I'm going to break those down. 4 and 3, 2 and 2, 5 and 3. All right, so I got a pair of 2s and a pair of 3s. So that's 6 I squared radical 5. What do we know I squared is? That right there is -1, isn't it? So that'd be -6 radical 5. If we jump the gun and multiply -12 times -15, we lose the I and thus miss the sign. And we would get +6 radical 5, not -6 radical 5, and that's not the same number. It looks close, but it's not really that close. All right, I want to show you some addition and subtraction of complex numbers, and then we'll do some multiplication of complex numbers too. All right, so addition of complex numbers. So adding, we'll also say subtracting, multiplying, and dividing complex numbers. Complex hashtags. All right. What letter are we on here? I started my numbers over. 3 plus 5i. That's a complex number, right? Plus 6 minus 2i. That's also a complex number. Adding them is just like adding polynomials. Put the like terms together. 3 plus what part does it add to? 6. 3 plus 6 will be 9. 5i plus -2i. 3i. And there's our complex number added together. Like terms. Subtracting is exactly the same idea. You subtract like terms. I want to show you a little bit of a trick with your graphing calculator. If you ever doubt yourself on the addition, subtraction, multiplication, or division of complex numbers, your graphing calculator can help you out. Okay? I can put in those two numbers. I can say 3 plus 5i. To get the I, you have to hit second and then the decimal point down at the bottom. Second and the decimal point gets you the I. And then I'm going to add, and I'm going to put the other complex number in parentheses. 6 minus 2 second decimal point to get the I. And then hit enter. Goodness. That's glorious. It's wonderful when things work out. That it will do complex numbers for you like that. It can handle that. It can't handle 3 plus 5x plus 6 minus 2x. It can't handle that. There's too many things that x could be. It knows what I is. That's why it can handle that. There are some that can do the x things, but the ones that you're legal to use in here, you cannot. It can only handle the i's. Okay. So if we take those same two complex numbers and we subtract them, for example, G, 3 plus 5i minus 6 minus 2i. It's simple enough to do by hand. 3 minus 6 is negative 3. 5i minus negative 2i would be positive 7i. Maybe that part's a little confusing. Can be done by hand. Could also be checked by the calculator. 3 plus 5i, parentheses, minus, parentheses, 6 minus 2i. Oops, wrong button. There you go. 3, negative 3. What did I do wrong? Yeah, negative 3 plus 7i. Calculator, also correct. Okay. That's nice. I generally do not use the calculator to add and subtract because I can do it just as quickly normally with my brain. I do use the calculator sometimes to do multiplication and division because there's quite a bit that goes on. If you go to take the same two complex numbers, 3 plus 5i times 6 minus 2i, if you multiply those, it goes back to the very first lesson from tonight. It's distributive property a couple of times. 3 times 6, 18. 3 times negative 2i, negative 6i. And then the 5i times 6, it'd be plus 30i. And then 5i times negative 2i would be negative 10i squared. Ooh. Then you got to simplify that. Not overly complicated, but it's still, you got the I squared in there you got to take care of. You got the I's that you got to put together. So there's several operations that could go wrong. 18 minus or plus 24i. And then what does I squared become? It's negative 1. So that's really plus 10. So I can put these like terms together. So that'd be 28 plus 24i. So after all of that work, I've got a complex number as the answer. If I did that in the calculator, 3 plus 5i, then close parentheses, open up another set, 6 minus 2i. Same answer. A little less heartache, a little less grief to get there. Much quicker, okay? And now I will do a lot of, if I'm doing just a few problems of these, I usually don't use the calculator for multiplication, always, unless it's like just random numbers that I'm not exactly good at my multiplication tables on. It takes a pretty good number to do that, but division, I almost always do them with the calculator, just because I hate doing what you got to do. With the division, if you take 3 plus 5i divided by 6 minus 2i, this is the work that has to happen to divide those by hand. And I got to do distributive property 2 times. And so that's 18 plus 6i plus 30i plus 10i squared. And then on the bottom, I got 36 plus 12i minus 12i minus 4i squared. And then I got to simplify those. Gosh. 6i minus 10. And I got to simplify another step after that. Excuse me. And this would be 36 plus 4. So I end up with 28 plus 36i all over 40. And then I got to break that apart and do 28 over 40 and simplify that, and 36 over 40i to write it as a complex number and reduce those. 28 and 40 both divisible by 4. Be 7/10 plus 36 and 40 both divisible by 4. 9/10 I. And that's what it finally ends up being. Gosh, that's a lot of work. A lot of places to make a mistake. So on the calculator, if I just go parentheses 3 plus 5i, close the parentheses, division, parentheses 6 minus 2i, hit enter. Now it gave me an ugly decimal. I don't want decimals, I want fractions. So I hit math, enter, unless you have yours already set to do fractions. I get messed up somewhere. 18. Oh, that's minus 10. So that shouldn't have been 28. Should have been 8. So that's where the 1/5 comes from. 1/5. That's where that's coming from. It should have been 8 over 40, not 28 over 40. That was a minus 10. 1/5 plus 9/10 I. Another reason why I do them with the calculator most of the time. With that. Okay. So the complex numbers, getting those, just use your calculator to help you on those operations with those. They're not, I'm not after you being just incredibly versed at doing math without a calculator, or else I wouldn't let you use one. So that doesn't make sense. All right, so there we have complex numbers in a nutshell. It really doesn't get any more complicated than what you've seen here for the complex number stuff. If you want to look at some problems, you can out of the book. I'm gonna write this up here. So that gets you some practice out of the book for what we've done here, and that'll get you kind of going with that.